if we have got some kind of symmetry, some kind of even distribution, we basically call it as homogeneous, right? So that's the topic, homogeneous differential equation. So we're just going to take few sample problems, okay, and we are going to understand it. I think that will be easy. And when we take this example, we can simply write it down as dy divided by dx. We have a differential equation of this form, and it might be a function of x and y on top, and it may be a function of x and y at the denominator as well, okay. And if we take some examples, okay, of a homogeneous differential equation, maybe one example I can give you like this: dy by dx is equal to y by x plus tan inverse of y by x. So you see there is a y by x, there is some kind of symmetry, the powers are same, okay. It basically comes under the category of homogeneous equation. I can also write some equations like x square dy plus y into x plus y dx. This is also a homogeneous equation, okay. Maybe is equal to, let's say, 0. This is also a homogeneous equation because the power of x is 2. If you take y and x, powers add up to 2. Y square is also there, the power is 2. So whatever is the variable, the power that they actually combined together take up is 2 square, okay. So this is actually some kind of symmetry that is there, and that is why it is actually homogeneous equation. Eventually we will see that as we keep on solving numerical problems for homogeneous differential equation, when we do use the technique to solve it, we'll see that these kind of equation becomes simpler and we can easily solve it, okay. I'll show you how we're going to do it. Now let me take one final example, maybe x cubed dy divided by dx, okay, is equal to y cubed, powers are 3, and this also you can consider to be symmetrical. Let me say it's y square and root over y square minus x square. Although I'm not separating out y square and x square here, but this is actually square and it's under a root, the power is 1, this is square, so square and 1 will become cubed, okay, and so on, okay. So in that way we can actually say that there is some kind of symmetry there, and that is why we basically call it as homogeneous equation, okay. So you have to just look into that symmetry part and then you can easily identify it, okay. This is a short way to identify whether we can use the technique to solve a homogeneous equation or not. So there will be some kind of symmetry, okay. So we just keep note of that, and based on that we can actually solve a number of problems. So let me just take one problem here first at the beginning, as I always do. I'm just going to solve it. I'm going to ask you to solve it right now, or you can solve it if you want. Very easy. Dy dx is equal to, I'll take this first sum only, okay, whichever we have, y divided by x plus tan inverse of y divided by x, okay. It's just substitution, that's it. Whenever we have a homogeneous equation, the technique is very simple. We have to do either this, put x is equal to vy or y is equal to vx. This is the only thing that we have to decide to solve the problem, okay. So if I put x is equal to vy, I will have vy square divided by x. So it's still a function of y and x, okay, and v does not help out. If we put y is equal to vx here, that x gets cancelled and it becomes a pure function of v. This is the only thing that we need to check, and if we do it, it should be easy, okay. So here, take care of this. I will explain this again. Put y is equal to vx. You might ask me, so when do I put x is equal to vi and when do I put y is equal to vx? How do I decide that? You have to look into the equation, put one of the substitution and check if it is getting simplified or getting complicated. If I put x is equal to vy, x is equal to v, okay, this will be vy square divided by x. So still it will be a function of y and x. I want to bring it in terms of pure v. And if that happens, it gets simplified. So if I put y is equal to vx, okay, I can simply write it down as dy divided by dx is equal to y, which is actually vx divided by x plus tan inverse of vx divided by x, right. So the x will just cancel out and I will actually have a function of only v. So it will be v plus tan inverse v. So on the right hand side we have got it as a function of v, right? So the things become simpler now. So let's say I want to find out what is dy dx now. Okay, so from here I can do it. Dy dx is equal to, so this is actually, you know, two functions here, v and x are two functions here. So I can take v constant and then I can take d dx of x, so that is 1, so it is v plus dy dx. Okay, I'm taking dy dx on this side, and this side it would be, x will be constant now, and I can just take it to be dv dx. So two variable system, right? So you can take it this way. Done. Then what I can do is I can put it here. Okay, let me just, not to confuse you, just put one line here. Yeah, I can solve it. So therefore we can say dy dx, we have just now found out it's nothing but v plus x dv dx is equal to v plus tan inverse v. So this v and this v will just cancel out, and then we can use the variable separation technique. So if you remember from the last class, the variable separation technique is simple. I'll take x together and v together. So this is tan inverse v and this is dv. Okay, so what we can do is take dv. I think I've taken it to be, okay, tan inverse I've taken, right? Let me not take inverse. Okay, inverse will be a bit complicated here. This example, I think I should not take inverse here. Let me just rub off inverse. I'll just take 10. It should be 10. Okay, 10 inverse, it will be difficult to solve actually. Just 10. Okay, just remember this. I've taken it wrongly. So this dv gone. So this will be dv divided by 10v. Okay, is equal to, just cross multiply. So dx divided by x, right? And then what, you have to just integrate and solve it, right? So we can integrate on this side and integrate on this side. Okay, then put a plus c there. Okay, and since there is no boundary condition, that c will remain as c. So dv by v, that means it is cod v, right? Cod v dv. So that way you have to remember a lot of standard integrals. What is the integration of cod v dv? Even I don't remember. Okay,
log of sin t.
log of sine v, correct? Yeah,
Sin t.
I don't remember it. I've written it, so I know it, right? So I'll just put that constant as c in terms of log, because I know this side also I'm going to get log. Okay, so that way we can easily solve it, right? So take this. This is log of sine v, and if you look here, my v originally में तो v था नहीं, so it's v, it's y by x after writing down. So this sine of y by x is equal to, you know, log of x plus log of c. Okay, and then if you just, you know, simplify it further, uh, everywhere there is a log, so you can just get rid of that log. Okay, you can just combine on this side. Log of x plus log of c would be log of xc. Okay, so this sine of y by x is equal to xc. This side you can take the single log of xc, and then you have this answer, right? So whenever you're writing down a variable, you have to basically write it down in terms of y, let's say. So y, we not an equation, not a variable, sorry. Y is equal to x sine inverse of xc, right? So that will be your answer. So this way you can solve it. Okay, the second part is easy. You have to just do the substitution and solve it correctly. Okay, let me give you just one sum here, and then you can just, you know, just practice. Very important. So I will give you one problem here, and you have to solve it. 1 plus e to the power x by y. It's practicing, very important. Okay, although you know the technique now, but if you get the final answer correct, then only you get your marks. X divided by y, 1 minus x y y dy is equal to 0. Okay, solve this and tell me what is the final answer. Okay.